Hello everyone, welcome to week 7 of this course. So it's now the second half of the course is starting, and in this half also the next 6 weeks we will talk about various new interesting topics and architectures and so on. But in this particular week is focused on applications. So we will talk about the applications of the kind of methods that we have discussed till now, and we have chosen 3 important applications. So question answering, dialogue, summarization. We will also give you some flavor of how do you do it for English and other languages together. So in this lecture and the next, I'll talk about question answering. Okay. So what are the topics for this particular lecture? We'll talk about what is question answering in general. We will start with one particular aspect of question answering that became very popular, that is reading comprehension based question answering, and then we will shift our focus towards open domain question answering. Okay, so we will see what do these actually mean and what kind of methods can we employ for solving these kind of question answering problems. So question answering is one task that has a lot of practical applications, and you would have seen now on search engines. So earlier when you would put a query, they would give you some results that they still do, but if you query is a question like this one, where is the deepest lake in the world, they actually give you an answer directly on the search page. So here you are told where, so you are given the answer and what is the lake, and you are even given some particular images, maps, etc., right, as an answer. So it's a nice search page that comes up for that particular entity. And you can use that for asking various questions, like during COVID, like people had a lot of queries they would typically ask, and you get a structured answer particularly from a specific website, and you can see how good or bad that website is, right? But with the disclaimer, this was only with a disclaimer always. So now a question is how do we typically solve these question answering kind of problems? What are the different flavors to that, right? That is what we are going to discuss. So when we say what is question answering, we want to build systems that will automatically answer questions that are posed by humans in natural language. So typically you have a natural language question and you want an answer to that, right? I mean, somebody should give an answer automatically to you, and that somebody has to be a system here. So we are seeing how we can develop a system that can automatically answer a natural language query. Now there are a lot of things that we can talk about, like when you are saying you want to get answers, like what are the places where the answer is hidden, right? What are the information sources from which your answer will come? So is it just a text passage? So you have a passage, you are asking only from that, or is it from all web document? And that is what will actually define our reading comprehension versus open to open question answering distinction. So when we say reading comprehension, we will have a single text passage from which you will be asking question. And when we say open domain, you can ask question from all web documents, all Wikipedia pages and so on. Or is it coming from some knowledge base, some like a graph? Is it coming from some tables, images, and so on, right? So what is the information source from which you want to gather the answer? Now what is the question type? Is it a factor type question, yes and no kind of question, just a fact? It's an open domain versus closed domain. Is it simple versus compositional? Your answer is compositional over, I mean, question has to have reasoning across multiple kind of facts. And what is the answer that you're expecting? Is it a short segment of text? Is it a paragraph, a list? Yes and no. So what is the answer that you're expecting, right? So this is how you can categorize your different question answering data sets and systems. So let's now move on to the reading comprehension kind of question answering. So why it is called reading comprehension? Because you are given a passage, right, and you have to comprehend that passage of text and answer questions about its content. So you are being asked a question: what language does Tesla study while in a school? And this is the passage that answers where he studied German, right? So your answer should be German. So it will be coming from that passage only. So you are given the passage, question, and you have an answer. And we briefly talked about that when we discussed how do you fine-tune BERT for span-based applications, and this was one of the applications we talked about, because your answer lies as a span in this entire paragraph. Okay, so here's another example. So where you're talking about Kannada language, and then other linguistic minorities in the state and so on, and you say, okay, question is which linguistic minority is larger, Hindi or Malayalam? So you see it's a bit more reasoning also involved. So you have to see Hindi is 3.3%, Malayalam is 1.27%, so Hindi is larger, right? So your answer is Hindi in this particular case. So the very popular data set that is used for this task is square data set. So that had around 100,000 passage question answer triplets. So and that became very popular because it's a huge data set, and that could be used for fine tuning large models, right? I mean, so you can even train them from scratch over this particular task. But many times you use pre-trained model and start fine tuning those. And these passages all come from English Wikipedia, and they were like not too long or not too small also, so 100 to 150 words. Now they used crowdsourcing to collect the questions and also the answers. So each answer would be a short segment of text, especially a span in the passage. Of course, that puts a limitation on what kind of question you can answer. You don't want a question where you have to actually take one span here and other span here and combine them. So it's only one span, contiguous span in the passage as your answer. So, and this was one of the most popular data set. But yeah, I mean, right now if you see it, it's almost solved. I mean, you have a very, very high accuracy on this. Right. So this is the data set. So we talked about it briefly earlier also. You have a passage and you have some question corresponding answers to that. Now, and let's talk about the evaluation metric also. So there were two specific metrics on which systems were evaluated. So when you give an answer, it can either be matching exactly or not. So you have an exact match matrix. So this is just binary. Either it is matching exactly or it is not matching exactly. But even if it is not matching exactly, maybe some words are similar to the ground truth. So you have a partial credit in F1. So now one interesting thing was that they didn't rely on a single ground truth. So they, specifically for development and test set, so they had 3 ground truth answers. Okay, for each question they had 3 answers. Now some of them may be same and some of them may be slightly different, because there are questions where multiple plausible answers are there. Now what do they do? So once a model predicts an answer, they will compare it to each ground truth, right? And while doing that, they will remove some A and D and punctuations, and they will take the max. So they will give benefit to the model. So if there are 3 ground truths and model is matching more with one of them, so it will be given that particular score, the max of any of the comparison. And then this is for one particular prediction, and then you take an average across all the queries in your test set or development set, and that's how you compute your exact match in F1 metric. So let's take an example. Suppose this is your question: what did Tesla do in December 1878? And these are the ground truth 3 answers. So one annotator said left garage, another one said same, and the third one actually gave a longer answer, right? And let's say your model predicted left garage and served and severed, right? So let's read it as severed, right? All relations with its family. So now we have to compute its exact match and F1 score, right? So you can see that. So it is not matching exactly with any of these. So exact match is a max of 0, 0, 0, that's 0. But the F1 score I can compute. So let's say from the first answer. So how do I compute F1 for the first answer? So first of all, I have to compute for the first one, what is the precision? So it has four words, and the ground truth has only 2 words. and 2 words are exactly matching out of 4. So, precision is 2 by 4. What is the recall? So, recall is with the first one it could recall everything, right. Left crash is here. So, recall is 1. So, F1 will be 2 times P into R divided by P plus R. This is 1 divided by 3 by 2. So, this is 0.67, right. Now, second annotation is the same. So, even this one will be 0.67. For the third one, we will again compute. So, that will be, so what is the precision? So, this, as we said, is the same thing. So, it is 1. So, everything is matching. And what is the recall? So, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 words. You could recall 4 out of that. So, recall is 4 by 9. So, F1 will be 2 times 1 times 4 by 9 divided by 1 plus 4 by 9, and this will be 8 by 9 divided by 13 by 9, 8 by 13, right, and 13. So, this is roughly 0.61. Right. So, this is the 3 things. So, you have F1 as max of these 3 things, and that is where you get 0.67. So, that is how you do evaluation for a squared kind of data set. Okay. Now, what are the methods that people have used? So, we already talked about this method. So, you can use BERT for reading comprehension, where you will give the CLS token, question, separator, and the paragraph. And your goal is to find the start and end span within the paragraph, right. So, we talked about this, that we can have then a start token and end, a start vector and end vector, and we will take dot product of that with all the hidden states, and I can compute the probability using taking the softmax, and I will compute the loss, right. And at the test time, I will compute simply the, for a span, the WT start HI plus WT and HJ for the span, for a particular span. That is how I compute the score and take whichever span using the highest. And we also did a question on this, right. So, this is what this is how you can use BERT directly for reading comprehension. Now, there were many other works on how do you solve it better, like can you design better pretending objectives. So, BERT only used to predict one mask token, but now you are talking about predicting spans. So, what if during pretending itself we make BERT predict spans, right. So, we also briefly talked about this span BERT, but this has a direct connection. It helped in this squared kind of data set. So, what they did in span BERT, so they made a contiguous span of words. They masked contiguous span of words rather than masking some random words, right. So, you will mask some contiguous span, something like that would denote in a span, that would be a possible answer, right. So, you can predict this span from the corresponding context, and you have a very good contextual representation for helping predicting the span, right. So, this is what span BERT did, and span BERT is a good model for reading comprehension based question answering. Now, let us move on to the second kind of question answering that you want to talk about, that is open domain question answering. So, reading comprehension is very different setting. You are given a passage and the question, and you just need a span as the answer. In open domain, you are just given the question and the whole data set. Let us say entire Wikipedia is your source. So, my answer can lie anywhere on Wikipedia, but I want the answer to my question, right. So, then how do we solve this particular question? Like, I can't feed the entire Wikipedia on BERT and use the same kind of technique that I was using, right. So, we do not know where the answer is located, and it can be any question. So, I do not know which Wikipedia page the answer is, and once I know that page, where exactly is the answer. It is a much more challenging problem, but much more practical problem, right. So, how do typically people have tried to solve it? So, what do they see? Okay, they see it like a large collection. So, you have a large collection and a question, and you want an answer string, right. You want a string as an answer. So, you can divide this problem into 2 parts. So, one is a retriever. So, that is okay, from this entire repository of Wikipedia or whatever documents, you first retrieve some top k document that you feel are highly relevant. So this is called retriever phase. So from this given document and query, you retrieve some k passages. Now P1 to Pk are passages, not the documents, because you may not want to retrieve documents, but a smaller block of those. So you call them passage. And now given this passage and the query, now you want to get the answer, right. So this is a very general framework, and we will talk about many methods, and even the very famous RAG methods come under this. So you retrieve some relevant documents or the evidence, and then given the question and the evidence, you try to generate answer. So even RAG setting would come under this, right. So this and this can be solved using a reading comprehension problem. Like now you have a question, you can take each passage and answer, or you can generate answer, right. So you have a retriever and a reader phase. Now what kind of methods you can use in retriever and reader separately? In reader you can use many things. Like you want to just retrieve something that are relevant, so you can use even standard information retrieval methods like TF-IDF kind of retrieval methods, or you can train the retriever. So you can have a dense retriever that uses all these BERT kind of modules. And once you are able to retrieve, now you have a passage, you can individually see the passage, and you can use a neural reading comprehension model to find out what is the answer, right. And then you can have some way of so when you have multiple answers from different passages, you may have some way of scoring these, right, ranking these. So like this is one particular way. So you can say, okay, from all the documents, I'll define some fixed length blocks as my passages, right. So maybe it can be some 50 words or 100 words and so on, similar to what we had seen in the square data set. So like in this particular case, in the data set, you may have like 13 million evidence blocks with 13 million possible passages. Now each block can have roughly 2000 possible answer spans given a particular setting. So now how are you modeling it? You are saying, okay, so this is B is my block, and Q is my query, and S is my span. I want to score in a block a particular span with reference to my query. And how do I do that? I mean, first of all, this block has to be retrieved. So there has to be a retrieval score. So this block is retrieved from the query. So because I am retrieving some top 100, I will have some score for that. So I can have the retrieval score. Plus, once I have retrieved this block, I will find out the exact span. So that's where the S span will come into play. So I will have some score for that span, right. So I can combine these two scores in various ways. So a retriever score and reader score to give a score to this span. And now I can actually have over all possible blocks, all possible spans, whichever gives me the highest score is my answer, right. I mean, that's the general way you can formulate this problem. You can of course use a more generic function here, that it can be a function of the scores given by your whatever the embedding given by the two modules, and then you want to do some argmax over all possible blocks or all possible spans. And you can use various things for doing things much more efficiently, like how do I actually limit the number of spans that I can use, right. I mean, so if you try spans over all the blocks, that will be like huge. You don't want to do it over all the 13 million blocks. You want to limit this number in the first stage, so that in the second stage you have very limited things to work with. Okay. So the retriever component, what it will do, it will take the query, and it will take each evidence block that you have and use some method to find out which of them are relevant or look relevant and which of them do not look relevant. This is like one particular method that we will talk about using dense retrieval, where we will use the BERT embeddings, but you can also do it using BM25 kind of embeddings. Now once I have selected some evidence blocks, I can again use the reading comprehension kind of model, that I have a question, I have the block, and I want to find out what is the start and end of the span. So I can compute the hidden vectors for start and end, and then I can have some MLP to give me a scoring, right. I mean, that is another way that you get the start vector n vector for the span, and then you have another MLP on top to say, okay, how likely is this to be my final answer span, right? Rather than doing a dot product with the start and end vector. That can be another possibility, right? So this is how you can do retriever and reader, right? So now let's go into detail of what methods we can use for retriever. So we can go for some simple TF-IDF kind of methods also. So now you may have some idea about what do we do in information retrieval through TF-IDF. So suppose you have a query and you have a document collection, right? And you want to search within this document collection, and the goal of information retrieval is to find out a ranked list of documents, right? You don't want to get the answer directly, but a ranked list of documents. That's a standard setting. So how do you achieve that? So you don't want to search in all the documents, the query. So you do some very efficient processing there, like you do an inverted index, create an inverted index, right? And from the inverted index, given the query terms, it searches for that, which documents are there in the inverted index for this query, and put some scoring method, that how do I score a document with respect to a query, and gives a score. And then once it gives a score to the documents that are there in the inverted index for that query terms, it sorts them, right, and gives you whatever number you want. You want top 10, top 100, so you can get that. Now, how do you score the document with respect to a query? So typically TF-IDF is one method. So idea is that I will use two different information to score how important a term is for a document. One is depends on the term frequency. So it is directly how often this word occurs in the document, and if it occurs more, so count TD is the number of times term T occurs in document D. If it occurs more number of times, I'll give it a higher weight. If it occurs less number of times, I'll give it a lower weight, right? And because I just don't want to increase it linearly with the count, I use a logarithmic weighting, log 1 plus count. Okay. But there are many variations of this formulation. And then the second thing is inverse document frequency. That is, I want to give I don't want to give a higher weight to a term that is very, very common. It occurs in all the documents, so it does not provide much information about the topic of this document, right? So some stop words, for example, occur everywhere. If you're talking about news, maybe India occurs everywhere. It may not give you, if you're talking about India news, the word India may not give you much information because it's occurring in all the news documents, right? But if you're talking about, if you are saying something about sports, it may not occur in all the documents. It will occur in only specific documents. So it may be more relevant to the topic. So what you can do? So you can use something like n is the number of documents divided by DFT, that is in how many of those documents this term T occurs. So this is called document frequency of term. So you see, if it is a common word, its DF will be high. For a rare word, its DF will be low. And so common word, if you do n by DF, its weight will be low, and the rare word, if you do n by DF, its weight will be high, right? That's the idea. So you give a higher weight to rare words and lower weight to common words, right? So you have two weighting criteria for a term. So how often it occurs in the document and how often it occurs in the entire collection. Use that to give a TF-IDF weight, so multiplication of TF-IDF, right? So that's how you weight a term. And you do it for both document and query, and just compute similarity over TF-IDF, right? So what you do? So you have a document vector and query vector, and you take a cosine of that, right? So this is how you compute similarity. So you normalize by the L2 norm over all the weights. So you have, so how do you score a document? You take for all terms in the query, you compute the TF-IDF weight for that term in the query and for the term in the document, and then this is the L2 norm that you divide by, right? That's how you typically score. Now, there are again various variations of this, like sometimes people say, okay, you are doing this IDF twice, so this weight that you are saying has been applied twice here, so you don't apply it at the query time or at the document time, so you only apply it once, otherwise it will just double the effect of this IDF, right? So that is one particular variation that is very, very crucial. Now otherwise, I mean, it's very straightforward, so we can see an example. So let's say this is my query. So two words, sweet love, and I have 4 documents. So sweet, sweet nurse, love, sweet sorrow, how sweet is love, and nurse, right? And let's say we'll do lowercasing, remove all these punctuations and everything. So I have 1, 2, 3, 4, 5, 6 words, right? 1, 2, 3, 4, 5, 6 words, right? And 2 words occur in the query and other, 6 words occur in the document. So what we can do, we can compute the TF-IDF weight. So let's see how do we do that. So this is a small collection of 4 documents. So for query, so we are computing TF-IDF, right? So let's say for all the 6 words, only sweet and love occurs in the query. So their count is 1, others count is 0, right? So this is my term frequency also. Now, so I want TF-IDF. So this is my TF. Now what will be IDF? It will depend on DF. So what is the document frequency for each word? So sweet occurs in document 1, document 2, document 3, right? 3 documents. So remember, it does not depend directly on how many times it occurs in a document. So even if it is occurring more than once, it doesn't matter, right? So I'm saying it is occurring in 3 different documents. So its DF is 3, right? And now once I know the DF is 3, then I can compute IDF. So log of 4 by 3, right? And maybe it gives you 0.125. And then you do TF times IDF. So this is your score, right? So similarly, you do for love, because other words have a count of 0. So TF is 1. What is the DF? Love occurs in 1 and 2 documents. So you compute IDF, right? Log 4 by 2. And yeah, I remember log of 2 is 0.301. So this is 0.301. And then you do TF times IDF. So 0.301, right? So this is what your TF-IDF weights are. The final thing that you do is the normalization. So you say, okay, I'll divide it by the length of this query vector. And what is the length of the vectors? It's simply L2 norm, and you take 0.125 square plus 0.301 square and take a square root. That gives you 0.326. So you divide each of these by 0.326 and you get 0.383 and 0.924. And you can do a simple exercise. You can take a square of these and you will get a 1, right? So these are normalized vectors now. Now same processing you do for the document. So let's say we are doing only for 2 documents, right? For this example. So let's say document 1 and document 2. So document 1, again I can do the same thing. I have the count for sweet is 2, right? And for nurse is 1 and love is 1. Others are 0. So TF weight will be log of, so what is the formula we took? Log of 1 plus count. So but there are other variation. I think this variation is 1 plus log count. I think this one is 1 plus log count. So this will give you 1 plus log 2, that is 1.3, right? So we would so this is 1 plus log count is what is used for TF here. And similarly for nurse, 1 plus log of 1 is 1, and yeah, it becomes 1. And IDF, we have already computed IDFs, so I can just multiply these IDFs. So 1.301 times 0.125 gives me this, 1 times 0.301 gives me this, and similarly 1 times 0.301 gives me this. And then I do compute the document length by this, so 0.456, divide by that, this is my normalized vector, right? Now how do I compute the similarity? Now this is normalized, query is also normalized, right? So I can just do dot product of those. So I'll do 0.357 times 0.383, and this gives me 0.137. So 0.661 times 0.924 gives me 0.610. So I add these two, and this is my overall similarity. So 0.747, right? Now you can do the same exercise for document 2 and verify that you are getting this particular score as similarity. And clearly you see that document 1 is more similar than document 2. And let's say sweet love, sweet nurse love, right? Matching 2 words, it's much more similar. Sweet occurs more than once, right? So that's how you apply this. So you will do it for all the documents and sort them by this score and produce a rank list, right? So this is the original TF-IDF. There are various variations, like one we saw. You can do 1 plus log count or log 1 plus count. So already a variation here. And many things, like you can multiply this IDF only once, like rather than doing it twice. Yeah. Now another variation of this kind of matrix that is very, very popular, has also been the default method to try any retrieval problem. That is very good baseline, that you say, okay, I have a new model, yes, compare with BM25, and many times you will see on the first try BM25 may beat very sophisticated neural model. So BM25 has been a very popular baseline since then, better than TF-IDF. So it's a variation. Again, you have an IDF term, a weighted TF term, and you see there are new parameters that are coming like K and B. So it has two parameters. So this will adjust the balance between term frequency and IDF, and B will see how much is the document length normalization important. So there are two variations, and typically if you to put this K as 1.2 and B as 0.75, it's a default hyperparameter that you can use. Of course, you can vary, but these are two default parameters that give very good results. Right? So this is the document length, and you also use it average document length. Right? So this is what something new here that you didn't have in the TF-IDF. Okay, so these are the sparse retrieval methods. But the problem with that is that all these methods, BM25, TF-IDF, they work only where there is a direct overlap of the query words and the document words, because that's what you are retrieving, right, in inverted index. Only when a query word is directly present in one of the documents, you will retrieve that, otherwise you will miss it, right. So, and that means the user would have to guess what words were used in the document, right, then only the user can get the answer. So like here, like the user may search for tragic love story, but suppose in Shakespeare it has been written about star-crossed lovers, it would not match because none of the word is matching here, right. So we can do something more semantic, so where words can be matched to semantic way, and that's where we can use all the machinery that we have understood, right. We can use all these word embeddings, the encoders, RNN, LSTMs, right. So we can use those dense embeddings, and we can directly apply BERT, the latest thing that we have learned in the case of learning the representation for the entire sentence. You can use pass it through BERT and use representation from there. And that has been one of the best methods in the case of dense retrieval, that use BERT for this particular task. Now, how do you use BERT for this? Now, you can have again different kind of methods. Like this is the one that we talked about, that I can use a CLS token, I pass my query, separator, and a document, and this is where I get a final answer. I can just get a score here, that how relevant this document is for the query, right. That is one way I can do this. So I can use a simple scorer here, right. Now what is the problem with this approach? The problem with this approach is that now you see, if there was only one document for the query, it was okay, but now that there are like thousands of documents, so you will have to append the query with all the thousands of documents, right, separately, like every time this is a separate sequence, and every time you will combine that, and then you will get this score. And now think about multiple queries, right. So for every, if there are like 50 queries and say 10K documents, you have to do 50 times 10K sequences, right? That many sequences will be created by this. So I want to avoid that. I say, okay, what if I make them, disjointly embed the query and the document. So that's what is called a by encoder. So I have a separate encoder. You can think about it, separate copies of BERT that you use, one for query, one for document, and they may be fine tuned, so they may have separate weights also at the end. So you have a query encoder, a document encoder. So you pass query through that, document through that. Now once you get the representation of CLS, you just use the two different CLS representation to find how similar they are, right. So here you will only have to encode 50 queries, right, one each time plus 10K, right. So you don't have to do 50 times 10K different sequences, only 50 plus 10K sequences. So this is much more efficient. While this may be more exact, this is much more efficient, is what people have seen. And that's why bi-encoder is typically more popular in open domain retrieval than a cross kind of encoder, right, where you use both. Of course, you can use A when you have very limited set of documents. After the first phase of retrieval has gone, you have retrieved, then you can use A in some way, right. But right now we are just talking about retriever. So how do you retrieve? So that's where this B is more efficient. Okay, so what you will do, you have two encoders, one for the document, another for query. You encode the query and document separately. You get their hidden vectors, maybe the CLS token or any other way you want to get the encoder, like you want to use LSTM and all. You can have separate ways of encoding these. Now once you have the representation, you can take dot product. You can do other things, like you can do MLP on top of these two representations. So there are various variations again here. So people have even tried what if we do dot product, element wise dot product, and differentiate. I mean different operations over these. But the idea is that once you get the representation, you can play with that. You can apply various kind of networks on top of that to find the score, right? And there would be some way in which you can train the encoders. So yeah, I mean that is one way. I mean even if you don't train the encoder, if you think they are good enough for the encoding, you can directly use this as a score, right? If you're not training the encoders. Another very relevant encoder that is very recent is ColBERT. So where they again use a bi-encoder setup. So they have a separate encoder for query and the document. And once they get the representation, so that's where they differ slightly from the previous approaches. So what they are doing, so suppose you have a question and this has n tokens, and you have a CLS before and a special query token. So you have a CLS and query. So tell the model I'm encoding a query, right? You pass it through BERT and you get the n final contextual representations for the n tokens. Similarly, the passage, suppose it has m tokens, so you include a CLS and a D token for the document and also encode it and get that m different contextual representation. Now, so what you will do, so because these dimensions may be huge, right? Right now we are talking about taking dot product of these, but there may be 768 dimensions. So because you want to make use of all these encoding separately, not just a CLS token. So one trick that they used is that they apply a additional layer to reduce the dimensionality. So 768 they will take it to some small dimension like 32 or so, right? So to make it more efficient, right? So they make it a smaller dimension. And now what they will do something like max similarity. So each individual token of the query, they will find its similarity with all of the contextual vectors for all the document tokens and see which one is giving the highest similarity. And they will take that one, and that's how they will do for each query. For each query token, what is the max similarity for any of the document token? Right? It's like finding out what is the max similarity this word is getting from anywhere in the document and just sum that over. Right? So what they will do, so for a query in document, so this is like n is my number of query tokens, and for each query token, I'll take the embedding for that query token qi and find out its similarity with the jth token of the document, and among all the document tokens, I'll find whichever gives them the max value for this, right? And that is my answer for one query, and I'll do for n queries, and I'll add that, right? So this is another way of doing similarity between query and document. So now we talked about this dense retrievers, but the good thing about these, you can train them. So you cannot train a BM25 or TF-IDF model, use them off the shelf, but this one you can train. You can compute, you can backpropagate by the loss, and you can update the parameters. But the question is like, how do you get training data? Because typically in data, what you would have is just a question and an answer string, and you will know the entire collection, but you do not know what is the ground truth. That means given a question, which passage contains my answer, right? So you may not know that. You may just know the answer string. So how do you get training data for training this models, and what kind of training objectives will I use? So that we will discuss in the second lecture, so in the next lecture. So you can read more about this in the chapter 14 of our SLP3 book. Thank you.